Hello. In this lecture, we're going to start discussing decking. And when I say decking, I mean the deck boards, nailers, fasteners, crossbeams underneath, um, and everything that makes up the walkway that people and potentially animals will be walking on. So the first learning objective is to understand the forces on various decking components. The second is to actually be able to apply the NDS, and that's the National Design Standard for wood, um, for wood deck boards. At this moment, we're only going to discuss wooden deck boards in this section, but in the future, it will be updated for the steel decking calculations as well. And third, we want to be able to evaluate the decking drawing standards for stability. So the first step is to find the loads. The distributed load on the decking is going to be the dead load plus the live load. And depending what we're looking at, there might be no dead load, like a deck board, or there might be a full dead load, like a crossbeam. And we'll be using the ASD, or allowable stress design method, for this design. Now, for the live load, so should we be using a reduced or unreduced live load? Right. We should be using a unreduced live load because the area is smaller than that 37 cubic meters when we're looking at just a deck board or a crossbeam. So when actually defining our loads, we will have a distributed load and a point load. So like I said before, for the distributed load, that's just going to be our 4.07, which is not reduced because of our area, and that will be multiplied by whatever our tributary width is. In this example for the deck boards here, our tributary width is going to be how much load is picked up by each deck board, and this is explained previously in the basic suspended bridge design course. And our point load comes from the manual, section 3.1, page 22, and that's going to be a 2.22 kilonewton load anywhere between the suspenders. Now on this diagram here, you can see the total load I have here, and right now I'm just representing that as an area load, and it will get reduced into a line load based on our tributary width of our deck board. And our point load can be applied anywhere between the suspenders, but as you may be able to intuit, in the middle is going to cause the greatest bending force, and right up towards the edges is going to cause the greatest shear. And this ability to be applied anywhere between the suspenders can create a torsion force, like we talked about previously in the load section for wind loading. We will not be discussing that in this section, but it's just something to keep in mind when we are doing this force analysis. Something you can think about, that the code may prescribe only a 2.22 kilonewton load anywhere between suspenders, but as an engineer, you're responsible for thinking about all the conditions that can create for instability. So using the W1 detail as an example, our second step is going to be finding our stresses on our material. So here is a diagram of the detail, and you can see how that point load can be applied anywhere, and that distributed load will be turned into a live load that picks up a certain tributary area when we're referring to one deck board or one crossbeam at a time. So we have two options here. First, we could have a simply supported beam, which we'll consider that first beam here to be simply supported because it's fixed at the tower end, and there can be some elongation on the walkway side. As well, if you look at the details for W1, there is a 90 centimeter span at the beginning on that first deck board. Something else you can consider is removing the bearing on the nailer itself, which would be this portion here. Removing that bearing if we need to sharpen the pencil on the calculations, and that could bring our unsupported span down to 70 centimeters. But let's start with 90 centimeters because that will be more conservative. And for a simply supported beam, I won't go through the derivations of these equations, but you can see for the distributed and point load, here are our max moment, M, and shear, R equations to calculate the stress on that beam. Now we also can have a middle piece where the spacing between the cross beams is 1 meter, and then we can also reduce that bearing down to, for the W1 detail, 80 centimeters potentially if we were to take the nailer area out. Oops. But a middle piece is going to be considered a simply supported beam because as you can see here, the span can span two or three cross beams. So for a simply supported beam, or sorry, continuously supported beam, things are a little more complicated because the beam is statically indeterminate. And what does that mean? That means there are more variables than there are equations to solve. So we can get a shape that looks more like this red shape here, and all sorts of different shapes depending on where the load falls. So we'll use a more complex set of equations that come from the civil engineering reference manual. Once again, I won't derive them here, but you can if you want. And we have our maximum moment and shear for distributed and point load. Something to note, we will assume these are not happening at the same time. So we'll assume if the point load is actually the equestrian load, we'll assume that a horse walking over a section of walkway is not going to have the same live loading, is not also going to be experiencing a live loading on that section of the walkway at the same time. The final step is to check the allowable stresses. So one last thing to note is that we will just be checking bending and shear, and this is because of using some engineering judgment here. These are going to be the forces we think will govern. Things that we're leaving out from this check in the next section are the fasteners, so checking the lag screw capacity, as well as the nailer. We won't be checking the nailer, but something to think about is the actual bearing of the deck board on the nailer, and is there enough capacity here, bearing capacity of the deck board on the nailer to support the loads. In the next section, we won't be checking fencing details, but that will be another part of this module. And we've already checked our suspenders in the basic design course, and we won't be revisiting that here. It'll be the same check. And finally, the way we'll go about doing these checks are using a demand capacity ratio, which is the same concept as ASD, allowable stress design. We want our adjusted capacity, which is adjusted based on the code you're using and material you're using, to be that divided by our actual stresses experienced should be greater than 1.